So as usual, if you have any questions, feel free to throw them in the chat or just unmute yourself and speak up and ask it. But either way, I'll be looking at the chat as we go. So a couple of quick announcements. So we're underway with the inverse kinematics lab. This is one of the more difficult labs that we have to do. So if you are running into trouble or something is confusing, that's okay. Just take advantage of the piazza and the course staff because we are here to help. So this one is due next Tuesday, which means that we'll be spending tomorrow's lab periods on it. And so a couple of quick hints though from stuff that we've noticed as like the support staff. So first one is that this target position variable, target pos on line 29 is not for you to adjust. Some people are using that as the robot's goal position. When you do that, if you change these values from infinity over here, that prevents the wheels from getting set to velocity control. So in Weebots, your motors can either be position control, where you will call set position and then give a value, and it will turn the motor until it hits that position. Then the other way that we can control our motors is through velocity control, where we get to set the velocity and then it'll just turn continuously at that rate. So that's what we want for our robot, whether it is the Epoch or the Turtlebot. And so if you set those to position control and then try to set the velocity, nothing will happen. So for those of you who are seeing problems where your robot is not moving, first check to make sure that you've not messed around with this target pos variable. So if you are looking for a variable to use for your robot goal, you can just make something called goal position and then set an X, Y, and theta for that to use in your sources of error computation. So another thing that might be helpful is this pose theta that you set as your goal. You don't have to start setting that, right? Because that's just going to be factored into your heading error. And so while you're testing your feedback controller, you'll probably want to start by just testing your distance and your bearing error to make sure that your robot is able to at least get to somewhere that you tell it to go. And then not worrying about heading until maybe later once that's already operational. Because if you try to do all of this stuff at once, it might be a little bit trickier to debug. One other area of confusion has been what the inverse kinematics equations give you. I'll talk about this in a little bit more detail on the next two slides, but the IK equations are just telling you the total amount of wheel rotations that you need. And so it gives you phi L and phi R, which are not the same as phi dot L and phi dot R, which is the rate at which you want them to move. And again, we've talked about how your while loop is going every like 32 milliseconds or so. So your wheels can't actually turn as fast as would be needed to resolve all of this rotation at once. And so that's why we're able to use a feedback controller. So with that, it only matters that the phi L and phi R values are like approximately proportional to how much we have to go. So it doesn't have to be exact values because we're updating our estimates every single time through that loop. And then that brings me to the last point. One of the to-do items in the lab is to figure out values for x dot r and theta dot. In other words, the amount that your robot has to drive forward and the amount that your robot is going to need to turn. And so in the lab instruction, it tells you to set the x dot r equal to something proportional to distance error. So you can just set x dot r equal to that. You can pick some kind of coefficient that reduces the importance of distance error, and your controller should still work. The idea here is that we're taking those actual sources of error, and then we're coming up with some determination of which ones are more or less important at any given moment. So we'll come back to that in a couple of slides. Another topic is lab regrades. So we've gone through a couple of the ones that you've alerted us to. So if you do look at your grades and something is surprising to you, then please reach out if you think that it deserves another look. I'd be happy to do that. We've had a couple of issues where things have just been misgraded, either because the controller wasn't set up properly on the robot, or maybe the directory structure wasn't quite right. And so the graders saw maybe a robot that didn't do anything when you've actually completed the assignment. It just some silly mistake like that forced it to not work. So we're happy to go in, do the little bit of extra effort to get that to accurately reflect what you put into it. And then lastly, as always, if you're having any team issues with your lab, please let us know either on Piazza or via email so that we can solve it before Lab 4 starts next Wednesday. Any questions before I move on to our kind of recap of what's going on in Lab 3? Okay, cool. So if anything comes up, just throw it in the chat and I'll get to it. So here's our course roadmap. We are now on lecture 7. So we are over here, which is well beyond the kind of the low level stuff. I know we're still implementing inverse kinematics, but now we're starting to talk about the higher level behaviors. So these are things that directly are going to relate to stuff that you'll probably want to think about for your final projects. So these high level ideas about planning, about how to do sensor interpretation or multi-sensor fusion are pretty independent of the underlying robot apparatus that you're using. And so now, as long as you have the terminology and the general knowledge behind or intuition behind forward and inverse kinematics, it doesn't really matter if you're using the epoch or if you're using a quadcopter or if you're using some kind of manipulator arm. It's all generally the same concepts. So now we can start talking about getting some of these more interesting higher level behaviors up. But before we go on to today's material on planning and world representations, just a really quick overview of the inverse kinematics lab will be beneficial from what we've seen so far. So in particular, we feel that everybody's fairly confident with computing their sources of error. And the majority of the questions that we've gotten are about these update rules. So what does your feedback controller actually look like? And what does all of this mean? So what we're doing is we're taking our sources of error, and then we have to map all that stuff down into these two translation and rotation components. So how far does my robot need to move forward? And how much does my robot actually need to turn? And this is a little bit of a lossy signal. So if we look at this example on the left here, so this robot has to rotate, and then it's going to have to drive, and then it's going to have to rotate, right? So in order to do this in sort of like the shortest translational path. And so if we say that the amount of translation that has to happen is just this straight line distance, well, if we solve these things at the same time, we'd expect the robot to kind of take an arc that's going to get it to its final position. And the length of that arc is going to be greater than just the straight line distance between those 2 points. And it turns out that that's okay. So our translation will be wrong from this perspective of it won't accurately reflect the total distance that the robot is actually traversing over the course of that whole path. But the fact that we compute it every single time step means that it's converging towards the correct behavior. Because eventually our rotation will zero out, and then we will only be driving forwards. And so those things will become equal. And so when you're coming up with values for these, to map your sources of error down to something that your robot is actually going to enact with its motors onto its wheels, the important thing to consider is the relative importance of these two terms. So of course, you want your translation to be related to your distance error, because that's how far you want the robot to move. And of course, you want it to be related to your rotation error, or at least your bearing error, so you eventually start pointing in the right direction. But what you do with these functions, subject to the constraint that you're actually keeping in these sources of error, you can multiply it by whatever coefficients you want. So you could say that your theta dot is your bearing error squared, or your theta dot is like your bearing error cubed. Probably don't want to square it because then you'll lose your negatives. But some kind of exponential or whatever you want to do, right? As long as you're keeping the absolute sign, because it's just going to affect how important that signal is when you pass it into these inverse kinematics equations. So let's say I take my theta dot and I multiply my bearing error by 1,000. So now, if I had to, let's say, turn maybe pi over 2 radians, that gets scaled up. So now my robot's going to think, hey, I have to turn 500 radians for my rotation error. And if I put that into these equations, then that's probably going to drown out any translation error that's there, right? Assuming I don't put an equally large coefficient on this. And so when that happens, well, you can treat the x dot r as more or less 0. And what I'll get is some really negative value for phi dot L and some really positive value for phi dot R. And the net effect is that when I scale that back to however much rotation I can actually accomplish in one time step, my robot will just turn in place, right? It'll completely ignore that x dot R term because it's just insignificant compared to the other term on top of here. And the way that I'm able to do this at all is by treating this as a proportion. So I can get whatever values I want out of these inverse kinematics equations, and you'll get large values, right? Much larger than your wheels can actually turn in one iteration or 32 milliseconds. And so in the lab, what we're doing is we're figuring out what the relative speed should be by dividing the one by the other. And so that's why these lowercase r's disappear from us, because they're in both equations. And so if we take a ratio, those get canceled out. And so if let's, for example, my right wheel needs to turn twice as fast as my left, or twice as far as my left, then I'll just set my right wheel to 100% and I'll set my left wheel to 50%. And so we're doing this mapping again from the total amount of rotations that need to happen to some kind of proportion. And that proportion is going to get multiplied into our max speed. And that's how we go through this system, right? So we have some sources of error and we eventually map that down to wheel speeds. And we're updating this constantly. And as we do that, we're never really going to get too far away from our goal. So we're always going to be converging towards our goal, which was the initial plan. So we have 3 problems that you're going to have to overcome with your feedback controller values. So the way that you handle your distance error and your bearing and heading error. So one of them is this first point where they saturate over low values of delta t. So in our case, each iteration of our while loop is 1 delta t. Your wheels can't move that fast, so we have to do this proportionally. If your distance error that you feed into your x.r and whatever coefficient you multiply it by causes that to be a lot greater than your theta dot, the amount that your robot needs to turn, then the angle part is going to be ignored and your robot will just drive straight ahead. And so obviously that's not a good idea. If let's say your theta is pi, so that would say that your robot needs to turn around 180 degrees. Well, if your x.r is a lot greater than pi, then you're never going to see the difference from these two parts of the equations, and so your robot will just drive forwards. And then the last thing to worry about is your bearing error and your heading error both influence the amount that your robot needs to turn. So when you're first coding this up, just make sure you deal with your bearing error. You can completely ignore heading error. Then when you actually go and incorporate heading error, what you'll want to do is incorporate some kind of conditional statement that says, hey, I only care about heading error if I'm within a certain distance maybe, right? Or come up with some criteria that will make you care about heading versus bearing. And once you do all that, you will have pretty much finished your IK controller, and then you'll be able to program in the different waypoints to actually show that you can create a path plan with that. So now that we've gone through the summary once more, does anybody have any questions about any of the pieces of Lab 3 before we move on? Okay, well, I guess I will just assume that everyone is flying through Lab 3, and if anything is going wrong, then we'll address it tomorrow. Oh, okay, can we fix the bearing error before working on fixing the distance error? Absolutely, that is completely a design decision that you will make. So one way to set up your controller is to have your coefficient behind your bearing error to be really high. So again, like 1,000 times bearing error. And that's going to make theta dot really big. And that will pretty much force your robot to turn in place, right? Or turn with very little displacement once you do the correct proportionality of it. The downside to that is that your robot's movement will be like very rigid. So it'll turn in place and then it will drive forward and then it will turn in place. And so that'll take a bit longer than if your robot just does all of those things at once and charts a smooth path. All right, so speaking of paths, a brief recap of the motion planning material that we covered last week. So when we're talking about planning, we're always talking about generating paths. So we want a sequence of waypoints or a series of poses from some start position to some ending position that obeys some set of specifications that we have. And this is intentionally open-ended because, well, path planning is a fairly general concept. And when something becomes a trajectory, we're basically saying we have a path, and now we're also parameterizing it by time. So now we have some kind of temporal mechanics at work that will tell us how we want to go from one of these waypoints to another one. We drew this diagram, right, where we have our robot in the environment, and if we want to actually have, say, like a collision-free path planner, there are a whole bunch of components that actually have to come together in order for us to do that. So the robot can exist in the environment, but the robot needs to understand aspects of itself and the things around it, right? So we have the robot's internal sensors, and then we have some maybe external sensors that tell us something about the environment. Our robot's internal sensors can help us achieve some kind of desired motion, right? So just like these feedback controllers that we're building now. Those feedback controllers need a goal position. And so that goal position can come from some trajectory planner. And also those temporal dynamics can be fed in from one of these, from this kind of box over here. And if we have more than one position that we want to get to, then we need some kind of full motion planner to give us all of those waypoints. And so even doing something as maybe as fundamental to our robot as just moving through space requires a whole bunch of different components, and you have to factor in a whole bunch of factors. Okay, so we talked about these different spaces that our trajectory is going to exist in, our paths are going to exist in. So we can talk about the operational space. So that's just the physical world where your robot takes up some amount of volume and looks maybe for this 2D Claude robot looks like that. And then every graph of this, right, or every picture or snapshot of something in the world is just one point in a configuration space, where a configuration is defined by the angles of all of my joints. And then an entire path through my configuration space is a trajectory. And so a trajectory is just one point in some infinite dimensional space that can then map back down to a sequence of configurations, which maps down to physical points in space. And so when we talk about creating trajectories or doing something useful with them, we typically go through some kind of optimization process. And search is also related to an optimization process, which is why we bring it up. So we have some idea of a cost. So our cost function takes in our final solution and tells us how good it is. Now, there could also be constraints on that. And if we're talking about planning, then our constraints are that we start in our start state and that we end at our goal state, subject to some temporal requirement. So I have to define, say, capital T. And I don't necessarily need to just arrive at my goal state by capital T. If I have a path to get to my goal state in fewer steps, then hopefully in my objective function up here, I could say something like, hey, you get penalized for however many steps you take that aren't at the goal location. And that'll force it into a distance optimal, or at least length optimal solution. The question in the chat is, does the operational space only collapse to a single point in configuration space for holonomic systems? Yes, that's exactly right. So it depends on your frame of reference for this one. So if you have some kind of inertial frame of reference, and we're considering, say, these two joints that we have control over, theta 1 and theta 2, to be my left and my right wheel, then those are not going to map back to a unique spot from my inertial configuration. But if I actually just take a look at, say, where that joint is on my robot, so I have like that consistent frame of reference. So like, for example, you're just looking at the robot model in Weebots, that will map back to that same picture every time, right? Because it still will be a particular rotation or orientation of that wheel. So again, totally depends on your reference frame. Most of the time we're talking about like from the robot's perspective. So like self-contained within the robot, then yes, it will, like a single point in my configuration space will be a single like viewing, I guess, or picture of the robot itself. So here's an example of an optimization process with a cost function that's been visualized. So the cost function is a higher cost for areas in yellow and red and lower cost for the areas in blue. And so we can start with just like a rough guess of what a solution could be. Even if this solution doesn't really abide by all of my constraints, the closer I am to the final answer, the easier that this process will be. And so as I run this optimization process, we'll see that here it's taking this and it's searching locally for little modifications to this path in order to find a lower cost answer. And so it pretty quickly arrives at a reasonably low cost solution. It avoids all of these big like hills or whatever these negative costs represent, or penalizing costs represent. Let me walk through this example, right, of this set of possible Do we know what how do we know what reasonably low is? Reasonably low in which context? I see. Okay, so how do you know when you have a satisfactory solution? So that's something that's going to be highly dependent on the cost function that you specify. And so you could set up a cost function such that it has a penalty of 1 million for not reaching the goal state in time, in which case, if all of your other components of your cost function have ceilings that are relatively low, then you'll know that, hey, there's no way this thing could have gone over 1 million if I didn't violate this, this constraint of mine. And so totally something that you have to define yourself. And you also get no guarantees with this, right? Because it's not a global or optimal solution. It's doing a local solution based on your initial response or your initial guess of the solution. Cool. Okay, so we talked through this example about why it's hard to specify these optimization criteria because, well, if we're not careful, we'll get our car to drive over greenways, through buildings, et cetera, and encoding all of these costs to make sure that it becomes a good driver and respecting other road rules and all of that is some of the hardest parts of this particular formulation. But we can do it. And once you see, right, that your robot doesn't obey some particular criteria, you can just go back and iterate and then make it work out. But all of this was getting us to this point, right, of how do we get our robot from some start state to some goal state, whether it's a Sparky platform, an Epoch, a Turtlebot, a Tiago, you name it. So one thing that we noticed was we can't really do this with the tools we have thus far. So if we just put our inverse kinematics controller onto this problem, and we try to go from our start state to our goal state here, well, it's not doing any long-term planning, right? It's just kind of greedily moving along in whatever direction we tell it to. And even if we put in some kind of like path or like collision avoidance with our distance sensors, then it's still going to be possible for us to get stuck in different places if we get unlucky with the way that our environment is shaped. So for example, if we get stuck in a U-shaped object, well, then our robot's not going to be able to make it out, right? Because there's nothing that's going to tell us how to find the exit. And so we need something better than this. Right? We need something that actually has that look ahead that's going to tell us if we do have a satisfying solution available to us. And so here's where we ended last time, which is specifying our goal, right? So we want to find a collision-free path for our mobile robot with a bunch of static obstacles. And we went through our input. So we need the geometry of the robot, the obstacles in the environment. We need to know about the kinematics of the robot so we can formulate our equations. And then of course we need an initial and a goal state. And that's the thing that we're actually using or plugging in to solve for. And hopefully we get out some continuous sequence of collision-free robot configurations. This sequence should connect our initial and our goal locations. And if we follow this sequence, then we should actually be able to traverse the space to get to our goal. And the way that we do this, without having to invent all kinds of new algorithms, right? We want to be able to apply the path or the search algorithms that we already spent a bunch of time learning is going to be to convert our problem into a format that is accessible by those methods. And so we introduced this notion of configuration space a couple of lectures ago, where we have instead of looking at things in X, Y, and physical space, we just look at the motor positions for our robot. And this makes things very convenient for us to plan it. And so we just have to figure out now, how do we avoid obstacles with this particular formulation? So we're going to need to put obstacles into our configuration space, or come up with some mapping such that if I know, for example, where something is in the physical world, well, which configurations of my robot are no longer available to me, right? So for this two-link arm, which configurations or motor positions are going to cause me to collide with it? Because I shouldn't allow myself to actually use those. And if I know where those are, I can apply some kind of search algorithm in this space, right? So let's say I wanted to get my robot to a particular pose. Well, I want to make sure that I don't go anywhere in this red region, because otherwise I'm going to be colliding with this obstacle here. And so we'll go through a couple of examples of how this works. So here I have my configuration space. So let's say I have a robot that's just a triangle that can freely translate on this plane. And I have some obstacle O. So the way that I turn this XY plane into a configuration space for my robot is going to be to extend the obstacles out. So for example, I take the shape of my robot and I basically just append it or union it with all of the obstacles in my scene. And so now I've buffered my obstacles by the size of my robot. And so now I can just treat my robot as a point, right? Some point mass in this space. And if I do that, I can apply any of my favorite search techniques, right? Because those don't require me to do collision checking anymore. I just have this notion of free space or occupied space. And so I just say I can't go into any of the positions where I'm in collision with an obstacle, which would be any of this new C optical, and I'm good to go. So now let's take an example with a circular robot. So this looks a lot like our epoch or our turtlebot. So I have my notion of free space, I have my notion of obstacle space, and let's say that this robot is holonomic. What would I change about this graphic in order to make this into configuration space as opposed to my world space here? Okay, so that's the first one. I want to make my robot a dot, right? So just treat it as a point object. And what do I have to do in order to accurately do that? Yes, okay, so I can enlarge each object by the radius of the robot. And if I do both of those things, now my world looks like this. And so anything in yellow or black are spaces that I cannot plan in because my robot would be in collision. And so now I can just treat my robot as a point mass and apply whatever search techniques that I have handy to solve this problem. And so we can see as your robot gets bigger, you have to extend your objects more and more, which can limit the feasible space that you have to plan it. Okay, so these are all good examples for the holonomic, or sorry, the holonomic case, where your robot can freely translate around. What about if my robot is, say, non-holonomic, or let's say it's orientable, and so that means my robot can rotate around. So let's take this example. We'll go back to that triangular shaped robot. And so now in XY space, right, in my world space or task space here, I have this path of my robot. What is that going to look like in configuration space, right? So I have these obstacles. I have my X and my Y axis. What will my axes be in configuration space? Okay, so I have an X and a Y and a theta, right? So my robot can translate around the space and can also orient itself. So I have an X, Y, and a theta. So I have 3 axes. And my configuration space is going to look like this now. And so the idea, right, is that for any point in my configuration space, right, that's going to translate into some point in my world space, right, some unique point over here. And all I'll do is just check to see, am I in collision with anything? And that's going to be represented by these kind of like twisting pillars of obstacle. And so this is what configuration space will look like for this 3 degree of freedom mobile robot. Now, it gets a lot harder to think about, and it's certainly impossible to visualize this once you start talking about, say, 7 degree of freedom robot arms. But the concept is roughly the same, where we have one configuration of your robot, right? So let's say 7 joint angles for that 7 degree of freedom arm. And that's going to put it into some situation in its world, right, in the physical world. And if it's in collision, then maybe we'll just color in that particular point as saying it's occupied space. And if it's not in collision, then we'll just consider it free space. And so we should be thinking about this problem as fairly computationally expensive, right? If we want to actually build this diagram, that's going to be a problem for us, right? Because that's going to take a lot of time to fill in every single point of that 7-dimensional space for us to plan through. And so typically speaking, we don't want to have to compute all of that way ahead of time. And so we'll come up with a couple of strategies for getting around that problem through the rest of today. So to recap all of this, if we worked in the task space here, right, in like the actual physical world space, then every time we take a step, we have to check for collisions between our robot and the obstacles in the space. If we operate in configuration space, we've kind of done all of that collision checking in advance. So we can just plan through space. And if we know what our environment looks like ahead of time, then this can be a one-time cost that we settle up, as opposed to this condition where I'm basically doing all of that stuff online, and that's going to slow me down. If anybody has any questions about this concept or it's not terribly clear to you, please send me a message in chat, just so I know whether or not to spend a little bit more time discussing it. Okay, so we have our search problem. How do I get from start to end? What's going to be problematic with just applying something like Dijkstra or A star to this? Can anyone think of a reason why that might be challenging?
It's continuous.
What makes it too expensive? So let's say my space is just XY here, and my robot can be just freely translated. Let's say I have a holonomic robot, right? So I can translate XY however I want. What's going to prevent me from just like applying something like A star to this problem? Okay, so you needed a lot of nodes, or what's a node? Okay, so yeah, so we'll explore this concept, right? Of like I need a lot of nodes to account for potential positions. Well, this is a continuous space, and so I can't just apply an algorithm like A star to a continuous space. I need some kind of discretization of my space in order to act within it. So if I drew a grid over this, then maybe I could apply something like A star. But then the question is, how big do I make my grids or my grid boxes, right? So if I make my grid boxes really, really small to accommodate spaces like this, then it's going to take me a very long time, potentially, right, to actually search to figure out a path like this one. And so the big problem that we have is we have a continuous space, right? The world is continuous. And I'm trying to figure out how I can apply discrete algorithms to the continuous space. And so our problem statement is essentially we have to reduce some kind of intractable problem in a continuous configuration space to some tractable problem in our discrete space. And so the tools that we have available to us are environment representations and search algorithms that are going to use those environment representations to figure out a path from the start to the end. And so today we're going to talk about a couple of different environment representations that are pretty useful. But the thing to keep in mind through all of this is that when we're talking about planning, there's often a conversation about length scale. So what level of granularity is appropriate to plan at? So if we think about, let's say, the task of like getting up and going to the kitchen and like getting a coffee, you're probably thinking about planning at a high level, right? So, okay, I need to stand up. I need to navigate myself to that location. I need to make myself coffee. But that's not a complete plan. You can't actually execute that on a robot, right? The robot needs something like joint actuation. So that like high level abstract plan needs to work its way back down at some level to like muscle movements or the equivalent. And so when we're planning, we're often planning at different length scales, and that's going to require different tools depending on the job. But the important thing is that they all have to get connected together somehow. So if we consider an autonomous car as a representative example, some of the different length scales that we have to worry about for planning would be some kind of graphical representation, right? Let's say we can take a map and turn it into a planning graph by just putting vertices at every intersection. And if there's a road between those intersections, then we put an edge between those vertices, right? So like we can very quickly turn a roadmap into a graph. Well, a graph is something I can search over. And so that can become part of my planning solution. right? So if I want to figure out how to get from like Pearl Street downtown to the hill, I would probably start by looking at road navigation, like road level directions. But then there are other levels of planning I have to worry about. So more local planning problems, like how do I negotiate an intersection? So how do I plan across, say, a left turn? Where are the appropriate places for me to end up? This is a very different problem, right, than the one above it. And it's equally important for actually getting to my goal, but I don't want to solve the top problem now with this bottom, more granular approach because it might just take too long. And so I can come up with this like more granular waypoint, but then I'm going to need some other lower level controller, right, to kind of keep me on the road, right? How do I stay within my lane when I'm there? And so now we're getting to the point where we're just in a continuous space where I can't necessarily come up with a quick graph that's going to encode the different rules of the space. So if we're talking about this intersection problem, I have a fairly small number of choices, right, of where to go or which points there are going to be important for me. But if I'm just driving along the road and say there's some obstacle there that I want to avoid, I can't use these approaches anymore, right? So I'm going to have to go to some kind of sampling-based method to stay within my lane. And even further than that, once I get some kind of waypoints, and this is what we're working on right now in lab, I need to figure out some way to actually follow them. So that's where my feedback control is coming into play. So these top three steps all work towards getting me different waypoints or positions that I want to be in over time. Whereas this bottom one is the thing that's actually getting me between them. And none of these are terribly useful without the other ones. And so I typically have to think about the entire top to bottom, bottom to top planning pipeline in order to get my robot to do anything terribly interesting. Any questions about length scale variability and planning?
For our purposes, does a robot know like the entire environment, like their vision isn't limited?
So pretty much up to you, however you want to formulate the problem. So if you had like total awareness of your environment and like nothing was ever changing, then you might not need to do this kind of like sampling-based planning approach, right? To like because there won't be obstacles, or if there were obstacles, like you would know about them ahead of time, and you can pretty much do whatever like offline planning algorithm you want. So you could feasibly like just put a big grid over your space and say, hey, I don't care how long this takes because I only have to do it once. All right, so let's talk about map representations because this is going to determine how feasible our problems are to solve or not. And so this is one place where you get the opportunity to be clever and add a bit of creativity because that will significantly modify the problem difficulty for your search algorithm. So things generally fall into a couple of different classes of representation. So everything is pretty much a graph. Otherwise, you're dealing in continuous spaces. But we have a bunch of ways of creating our graphs. And so all three of these things are graphs. They're just represented a little bit differently. So for, say, our grid map here, we have a uniform sized grid. And this is a graph because each box is a vertex and it's connected via edges to all of its neighboring boxes. Versus something like this, which is a variable size grid, but similar connectivity is going to apply where this is just a vertex that is connected to this one, this one, this one, and basically all of its neighbors. So we can come up with different properties of these graphs. And so we'll talk through four particular ones: visibility graphs, roadmaps, cell decompositions, and potential fields. But the first one we're going to talk about is the visibility graph, which is pictured here. So the idea is that we have some 2D space, at least for this example. We have a start state and an end state, and we want to find the shortest collision-free path to get there. And so the idea behind the visibility graph is that we can use the geometry of our obstacles to limit the places that we actually have to search. And so it is based off of this principle that if there is a collision-free path between any 2 points, then there's going to be some polygonal path that bends only at the obstacle vertices. So a polygonal path is just a piecewise linear curve. So this inner line, this red one, that's approximating this blue curve. And so what this means is that if there's a collision-free path, say between 2 of these points, then let's see, we can't do this planning if we don't know our environment beforehand. That's correct. So you basically take a snapshot of your environment, then you plan on it. And so you might have to replan if your environment changes or your perception of your environment changes. But yeah, and all of this is conditioned on this idea that you know something about your environment. Otherwise, there's really nothing we can do. So for the visibility graph, if there were, so the first thing we would try is just a straight line path from start to goal. If there is no start to goal straight line path, then what this is saying is that the shortest path is going to be along the vertices of our obstacles. So if, for example, this obstacle were not here, then our shortest line path would go to this vertex and then a straight line right to our goal. Because that is not the case, we have to search a little bit further. But the idea is that we're going to construct some graph from our environment obstacles and then search over that graph to find our shortest path solution. And so here I have two different representations shown. So the one we're talking about, this visibility graph method, is hugging the vertices of our obstacles. This dotted line is something called a Voronoi path, which actually tries to stay as far away from obstacles as possible. And so here we can see at any given point, you are as far away from all of the neighboring obstacles as possible. Okay.
How would you actually construct the visibility graph or the Voronoi path? Like what algorithms would you use there?
Yeah, so to construct the, so to figure this out, you just have to figure out what the vertices of your obstacles are. So if it depends on like what kind of sensor data is coming in. So if you have a LiDAR, let's say, so you have like a point cloud of your environment, then you'll basically try to like fit some lines to like the exterior of each of your obstacles. And those lines will, like where those lines intersect, are going to give you your vertices. So that's just one idea. But pretty much anything that you can do to that sensor data that will give you like the exterior of your obstacles.
Got it.
And so the only difference between the visibility graph path here and the Voronoi diagram path is that a point on a Voronoi diagram is essentially like equidistant to as many other points around it as possible. So in this case, they are equidistant to all of the neighboring vertices. So like you wouldn't say that like this point was belonging to like this obstacle or this obstacle because it's far enough away. It's the same distance away from both of these. So the idea here is that it'll stay as far away as possible versus the visibility one, which kind of hugs the obstacles. So let's look at the algorithm for it. So I run some algorithm on my sensor data to get this environment map. So now I know what where my vertices are at least. And so now I'm just going to create every pairwise connection. So for every vertex, including my initial state and my goal state, I just try to connect them with a line. If that line goes through the obstacle, then I throw it away. That's not a valid edge, right? So that's why like this vertex doesn't connect to this one, and why I don't have any like self connections between my vertices here, except for these neighboring ones. So if I collide with an obstacle, I throw that edge out. And so this gives me a graph. And this graph is an approximation of my environment. And so I can use this graph in order to plan. So now I just can annotate, let's say I can weight these edges by how long they are. And then I can run my favorite path planning algorithm like Dijkstra or A* on it. And that should give me the shortest path through the graph. So in this case, the one kind of highlighted in bold. So here's more pseudocode, right? So I'm going to take in my initial state and my goal state, and then all of my polygonal obstacles. And again, like I can come up with these polygonal obstacles myself. That can be an approximation of the actual obstacles in the space, right? I can say, hey, I don't want to do any complicated like shape fitting. Maybe I'll just say everything's a square and then like fit a square over top of all of my stuff. I'm no longer going to be optimal, but maybe I don't care about that. It's just another way to actually use this kind of algorithm. So for every pair of vertices or nodes, if it's an obstacle edge, so like this, then I'm going to add it into my graph because I'm allowed to do that. Otherwise, I have to check every obstacle to see if it intersects with this line I'm trying to put down. And so if it does intersect, then it means it's in collision. And so I just ignore it and I go to my next pair. Otherwise, I insert that. And I can just do this and it will output my visibility graph. So I can turn this scene into this graph. Okay, so this seems like a pretty good idea, right? Like this is going to get me optimal path for these kinds of scenes, assuming that I actually know what my obstacles look like. So what are some of the weaknesses maybe of something like this?
What if we have a lot of different shapes and have to do a lot of computation?
Okay, so it might be tricky for me to actually get these like polygonal like representations of my obstacles. So yeah, that's definitely something that I'd have to consider. If my odometry is inaccurate, then it's really easy to run into things. Yeah, I mean, that's a pretty big weakness, right? If there's any kind of execution error whatsoever, like I'm going to crash. And the reason I know that I'm going to crash is because I'm going as close as possible to all of these obstacles, right? And so that's going to be pretty bad. It might make silly paths if I have weird geometry or small objects. Well, this will give me the best path subject to those obstacles, but it's going to look a little strange because we'll be hugging a lot of walls.
You can just inflate the geometry of the obstacles, though, to give you some padding room.
Absolutely. Yep. So again, I can approximate these geometries however I want, right? But that's the trade-off, right, of optimality versus practicality. What happens if I'm in like more than 2 dimensions? This blows up in larger dimensionality spaces than 2D. So that's one of our biggest weaknesses, is that if I have now that doesn't mean it's worthless. Like a lot of problems can be represented in a 2D environment. So that's actually not a huge limitation for us, but that is something that we have to consider, that this does not scale well to higher dimensional problems. And then in chat, circular objects, or really just like any kind of high poly object, is going to cause us to have an explosion in the number of vertices that we have to consider. And so unless we're really clever about that, that could be pretty bad for us. So yeah, good catch. All right, so that's visibility graphs. And the Voronoi mapping that I mentioned before, the Voronoi path, here's a figure that kind of illustrates what's going on or how that comes out. So Voronoi paths are going to take kind of an opposite approach, where I say, like, I don't want to actually be all that close to everything. In fact, I want to be really far away from everything. And so this approach will generate the path that maximizes my clearance between obstacles. And so here we have, say, a Voronoi map. So these are not actually related. These are not the same pictures. So here we have a bunch of vertices, so these black dots. And then this diagram is colored such that every color, or every pixel that shares a color, is as close as possible, or is closer to the same vertex. So everything that is this light blue color here is closest to this vertex, or at least closer than any other vertex. And so this kind of shows you maybe like a territory ownership map. And so what we can do is, on our environment, we can take those vertices and we can treat them the same as these vertices and just kind of color the map according to which vertex owns stuff. And then we'll also consider the boundary as being one of those vertices. And what we'll get is some boundary in the middle, right? And so we get this boundary in the middle. So this is as far away from everything as possible. And then we can plan over that graph instead. So this is a bit of an interesting way to go about with your planning problem. But let's talk about these strengths and weaknesses of this. So why might this be a good idea and why might this be a bad idea?
Does it decrease the amount of vertices you have?
So it could, like I can certainly take on less risk by sampling fewer vertices, right? Because I'm taking like so much clearance from my obstacles that it's probably okay. Okay, so longer path, yeah, definitely not an optimal path. Pretty circuitous.
The calculation looks really expensive.
It's pretty expensive to do this, yep. What about stability? Right, so what happens if a small change in my environment occurs?
You have to totally redo the whole map, wouldn't you?
Got to redo the whole map, absolutely. So we call that we call this an unstable representation, where small changes in the environment are going to result in large changes in my diagram, and so that's generally undesirable. So yeah, we talked about like the paths can be a little bit too conservative, and also this is pretty hard in high dimensional spaces as well, right? So like we're incurring a whole bunch more costs to do this. So that's why we typically won't do something like this in practice, but it's worth mentioning because it's kind of the opposite of the visibility graph method in terms of like idea. All right, on to our next one. So the next one is cell decomposition. And this is one that at least conceptually, I think we're all fairly like familiar with, which is just this idea that we can divide things into a grid, right? So we come up with some kind of discretization and turn it into some kind of grid format. But there's nothing that says that our grid boxes have to be the same size. And so just from a more maybe rigorous definition, we have two types of cell decomposition algorithms. So one is exact cell decomposition, which divides our space precisely, right, into some kind of like representation of the space. Or otherwise, we have approximate cell decomposition. And so we'll still usually have like regular shapes like rectangles or squares, but we're willing to like sacrifice some fidelity in our model in order to get some more convenient representation out. And so if we're doing something like approximate cell decomposition, then that's going to have us do some like different length scales. We're willing to say, oh, okay, like a little bit of that obstacle cut into that, that grid cell. So I don't care that much. It's only a little bit, I'll just ignore it. I'll pretend like it's not even in collision there. And so exact cell decomposition methods are guaranteed to be complete, whereas approximate ones, well, anytime we're approximating, we have to be a little bit more careful. The difference though is in cost. So if we're willing to approximate and assume that little bit of risk, we can probably save a lot of computation time. Otherwise, if it's extremely important that we're accurate with this, then our only option will be something exact cell decomposition. So let's look at an example of this in terms of things that we're going to care about for any kind of planning algorithm. So does everybody remember what a complete algorithm is, or what it means for a planning algorithm to be complete? You have to remember back to wherever you were taught things like uniform cost search and Dijkstra for this. So what does it mean for my planning algorithm to be complete?
Does it go over every possible path?
Yeah, exactly. So a complete algorithm is one that, well, a complete algorithm says that if there is an answer, I will find it. Right, so if that means going over every possible path to get there, then that's what that means. But it just says that if there's an answer, I'm guaranteed to find it. Now, you get no guarantees about how long it will take to find it, but you can just get the guarantee that it will find it. Then the other consideration we care about is optimality, right? So is something complete and is something optimal? So optimal is going to say you will find the best path. And so if something is complete and optimal, that says that if there is a path out there, I will find it, and the path that I stop on will be the best one. So it doesn't make sense, though, necessarily to just talk about search algorithms in isolation for this, because of course, our environment representation now matters too. So let's take this example. So I took my continuous space and I applied a cell decomposition to it. And here I see that there is no solution, right? I can't get from this red dot up to this red dot. And the reason for that is because I just didn't pick the right discretization, right? So I chose some kind of cell size and it wasn't good enough. There's plenty of space for me to go around the corner here, or like maybe even squeeze tightly through this one. But I picked my length scale and it didn't work, right? No planning algorithms will let me solve this. And so now things are no longer complete, right? Like it doesn't matter what search algorithm I pick because my environment hasn't allowed me to do that. And so one of the things that cell decomposition methods do let us do, if we take this a step further than this uniform size decomposition, is that we can choose like an approximate decomposition of the space. And any of our cells, right, that are occupied, we can just decompose them into, say, in this case, 4 different cells, right? So I can go through every single cell here and say, is this occupied? If so, I can divide it into 4 cells. If the entire cell is occupied, then I'll do nothing. And so for anything that's partial, I'll just split it. And then I'll do the same process. I'll iterate over all of those new cells. If those are completely full, then I just keep them as is. If it's partial, I split it. And if it's free, I leave it alone. And so with that, right, I can decompose my space into something that now has a solution. And so this act of taking my partially full cells and then splitting them up into smaller cells is something called quad tree decomposition. And so our algorithm is just as I mentioned, where we look and see like how much of my cell is full. And so this is a threshold that you can set yourself, where you consider something completely full or partially full or empty. And if something is partially full, you just split it. And if it's empty or full, you just keep it as is. And so you can represent this as a tree. And you can basically just keep going as far as you want until you maybe hit some kind of minimum length scale for each of your cells. Okay, so this is quad tree decomposition, right? So this is what happens if I'm in a 2-dimensional space. What do I do if I'm in a 3-dimensional space? What is an octree? How does that differ from a quad tree? Probably no coincidence that quad tree, so two squared, versus octree, 2 to the 3rd, right? 2 dimensions versus 3 dimensions. That's right. So for an octree, right, if I'm in 3 dimensions, then I'm just going to divide it into cubes. And I can just work my way down. And it turns out that this is a fairly good representation for, say, occupancy data if I have a large point cloud. So here's an example. Let's see if I can get this to play. So we can represent our environment as an octree here. So we have a whole bunch of different point cloud data points, and we can fuse those together. We can figure out what our free space is, what our occupied space is, and then we can apply that into some kind of planning algorithm. Right? And so even though we have a fairly large space here, we can use something like octree decomposition to give us a more sparse graph. Right? Because like the larger those cells are on my grid, or the larger those cubes are in my octree, the bigger step I can take for like one iteration of my algorithm. Right? So I have bigger steps until I get close to stuff. Then I have to worry about these like much smaller steps. So here's what our algorithm looks like. So we take our free space and we just discretize it by decomposing it into cells. So we can just pick some kind of starting length scale. So in this case, let's say that length scale is just half. So we're going to look at like our whole map, say, is this mixed or free? And then in this case, it's mixed, right? Because we have a couple of obstacles. It's not filling up the whole space. So I call this a mixed cell. So if that's the case, then I decompose the mixed cells. So I'll divide this into 4. Then I'll go back to step 2. I go through all of my different cells here. I see, are they mixed? Are they free? Are they occupied? I decompose the mixed ones, and I just keep iterating this until I hit maybe some minimum length scale. Okay, so what's good and what's bad about cell decomposition? So when do you limit the split? That's a good question. And so you could You could stop decomposing when there's a path. You could say that this algorithm, like that you stop when your cell size is becoming smaller than your robot, right? So like in that case, your robot couldn't navigate the gaps anyway, so why compute them? But yeah, that's a design decision that's up to you. And so poor choices of that can limit the applicability back to your algorithm. It's not as accurate as just treating them as polygons, that's right. But what do we get in exchange for that lack of precision?
Speed.
Yeah, it's pretty fast. It's definitely simpler to implement, right? Because I don't really have to know very much about my obstacles. I just have to know, are you in this cube of space or this square of space? So this method works in practice, which is pretty good, right? Like that's a really important thing for us to keep in mind, because a lot of things in robotics come down to, does this actually work in real life? And so this method does work in real life. Like it's making very few assumptions about the obstacles. Obvious solutions get found fairly quickly. It's pretty easy to adjust to changes in the environment, mostly because it's fast. So honestly, if we have to throw it away, it's not going to take us very long, assuming that our collision detection is reasonably fast. But there are some negatives to this, right? So the first one is, as we scale our dimensionality up, it stays difficult, right? Like it's going to get difficult and it's going to stay difficult. And also there's not really a clear notion of optimality, like certainly not a straightforward one. And so this is an approximation, and approximations are great because they let us act, but depending on what our design criteria are, this might not be the right solution. Okay, so now let's go to the last one, the potential field. So a potential field can be thought of as basically like creating some kind of topology where you want to just roll down the hill. And so in this case, we have an obstacle, and we have a goal, and it's defined everywhere. And so if I have a robot, I can just place it on this field and then just follow the arrows. And the arrows will all just lead me towards this goal. So this was initially proposed for real-time collision avoidance. And you can imagine if you had this thing defined everywhere and it was just available to you, you could just take a look and figure out which direction should I go in. So we have this scalar function over my space. So it's not going to be defined where obstacles are because I should never be there. So I don't need to actually know what that is. And then all I'm going to do is follow the hill, right? So find the negated gradient of the potential field at that position. One way that I can find that is just imagine that this is a matrix of numbers, right? Corresponding to an X and a Y position. And I can just look up the value where I'm at, and then look up all the neighboring values around me and just pick the direction with the greatest difference. Right, so I could just empirically calculate a gradient that way. And that'll just get me to roll downhill. And all of this is going to be defined by my navigation function, right? So the navigation function is something that creates those arrows, right? That's what I'm going to be using to figure out which direction to go. So in terms of generating a potential field, I have to have a navigation function. And I have some criteria that would make for a good navigation function. So it had, like, if I think, again, thinking about this as maybe like a topographic map is helpful. So the lowest point on my map should be my goal. There shouldn't be any local minima. So like there shouldn't be any small bowls in the environment that I can get stuck in. It should get infinitely large near obstacles to push me away from them. And most importantly, maybe it's smooth. So meaning there is a gradient, right? So I can follow this signal to just keep rolling downhill as I go. And so this was the idea of Osama Khatib, who is a fairly famous roboticist over at Stanford. And this is him up in the top right. And so the way that we make this work, right, we don't have to come up with this navigation function all at once, right? That would be really difficult for us. So we can decompose our environment into a couple of different sources of signal and then compose those error signals back together. So for, let's say, this environment, we have a rectangle and a triangle obstacle. I have my start position here and I have my goal position here. Then I can come up with two different components to my potential field. So I can just create this, this surface that just kind of gently rolls me from wherever I'm at towards my goal, right? So I don't really care where my starting position is. It doesn't affect this choice. All that affects this choice is where my goal is. I want to make sure that that's a global minima. And then I have my obstacles. And so I want to have really high costs around those obstacles so that like if I imagine my robot as like a ball, then as it gets close to it, it's going to roll away. And so I just union these things together, just add them together. And so I'll get a navigation function that looks like this, right? You can kind of see that it's already discretized. So you can just kind of look up the height and that will give you a value. And so again, if I just follow downhill, this will get me to my goal and I won't hit any obstacles. So this seems pretty good. What are my strengths and weaknesses here? How can this like lead me astray? And why is this a pretty good thing for me to have, or a good method for me to follow? Is this computationally expensive? Not necessarily. And we can like programmatically define cost as, like distance from goal. So the further away I am, the higher the landscape. And if I know where obstacles are, then I can set the cost to be really high at those spots and just add this together.
Is this good because it's like defined for wherever you're at? You don't have to like redo the search.
Yeah, so this is great. Because, one of the reasons this is really great is because it's defined everywhere. So if I have this and my environment like hasn't changed at all, I can just use this anywhere. So that's really cool, right? Like I can get relocated and I can still just follow this. So Andrew's saying, seems like it gets stuck in corners or U-shaped objects. So yes, U-shaped objects will create flat spots. So I could get stuck there. Another place that you can imagine getting stuck is if you have like a four-way intersection between obstacles, right? So that point in the middle is going to be flat. And so that could be problematic for me. A lot of computational locations that won't end up being along the path. So yeah, if I only have like a single query planning problem, then like I only care about solving this once and right now. So yeah, I'm doing some work for things that I won't actually use. Path isn't necessarily optimal. That depends on my navigation function. So yes, I mean, it depends on what kinds of forces are at play here. And yeah, so like there are places I can get stuck. But if my environment changes, it's also fairly quick for me to update it. So I really only have to recompute nearby those like whatever changed. So that's pretty cool. In practice, when you're using something like this, what could I do, right, to like get around this problem where, let's say, I get stuck in that four-way intersection problem? Like when I'm implementing my robot controller. So let's say I have like four squares and they all kind of are close to each other. So like I have occupied space over here, and then my only free space is in that four-way. Okay, so I can, if I treat those flat spots as obstacles, then that might compete with my navigation function, right? So the surface that's trending downwards. And so in that case, like I have these like traps essentially for my robot to fall into. So, but also like I can navigate through this, right? I just have to know that like it's okay to keep going. So what can I do to like avoid getting stuck at that kind of local minima?
When you get there, just continue with whatever speed you had.
Yeah, okay, so that's an idea, right? So if I hit somewhere where I've lost a gradient, right, I have no information to use, I can just use the momentum of where I've been coming from. Okay, so that could work. I could, though, come up with some kind of adversarial condition that might cause a little bit of trouble with that, right? So like, what if I just like put a U-shaped obstacle and like, let's say I came in this way. So it's a great idea, but we can take it a little bit further.
Can you just go back out the way you came until you have another viable path?
Well, I don't have this notion of other viable paths because I'm just following that hill down. So if I could backtrack, I would have to know when I'm done backtracking, which might be difficult, right? Because I'm not actually doing any planning here. But that is a good idea. Let's think about something simple, right? Because like I have limited information to work with because I'm not allowed to plan all the way to the end. Like I have to just use the tools that are in front of me. So what would happen if I just injected some noise, right? So I took the gradient and I used that to figure out which direction to go. And then I added maybe like some zero mean like Gaussian noise or like normally distributed noise to it. So now my robot's no longer kind of rolling neatly down the hill, but like kind of vibrating around down the hill. So if I do something like that, if I get stuck here, then I won't actually like stay stuck here because I'll have some like little bits of noise. And if I've chosen that parameter properly, right, like if I've chosen enough noise, then hopefully what would happen is eventually it would sample a value that kicks me out of this local minimum, and then I have another path that I can take. But these are just design decisions to make. Okay, so we'll stop here for the day just because I don't think we'll have enough time to really get into the next class of methods. But all of these things that we've talked about thus far are fully deterministic. So I follow the same process every single time, and my completeness guarantees are pretty straightforward because of that. And so what we're going to talk about next are probabilistic methods. So now we're going to forego, right, this consistency in favor of potentially reaching our goals faster. But we're going to have to think about a couple of things. So the first one is, can we get completeness guarantees? And the second one is, can we get optimality guarantees, even though we are using probabilistic methods? So does anybody have an idea of the answers to either of these questions? So can we get a completeness guarantee for probabilistic methods? Meaning, if there is an answer out there, I can guarantee that I will find it.
I don't think so initially, but I feel like there's some freaky way to do it.
Okay, good intuition. So when we're thinking about things like completeness, right? Like we're not really thinking in terms of like convenience. So we don't care how long it takes, right? I just need to have a proof that says like by the heat death of the universe, or maybe even after that, right? Like if I leave this thing going on for infinitely long, will it find it? And so like there are problems where we have deterministic methods. So for example, if you have a path planning problem that has, let's say there's like a trap that has infinite length or infinite like search depth, then depth first search will get stuck there, right? So like it'll never try other options. And so in that case, like we know that depth first search is not a complete method versus something like breadth first search, right? Where, well, it's going to search all alternatives. And so if the optimal path length is n, then by the time like we branch out and hit the nth iteration, like we'll find it. Now, if that branching factor is infinite, then that breadth first search will not actually work for us anymore. And so we have to be careful with how we define our problem, but we'll find that it is actually possible for us to get completeness guarantees with probabilistic methods, and the way that we do that is by saying there's some as long as there's some probability that something will happen, eventually it will happen, right? No matter how rare it is. So as long as there's non-zero probability that like this will sample the like best path, for example, then I can have some kind of completeness guarantee. Now that's not necessarily useful, but it is a first step. And so we'll come up with some clever ways to use probabilistic methods to come up with environment representations that we can then search on. But we'll leave that for next week. So I'll see you folks in lab tomorrow. If you have any questions, feel free to post them on Piazza, and we will break there for today.